Hello, this is Daning Huang from Penn State Aerospace Engineering, APUS Lab, and we have been doing some AI and machine learning stuff for multi-physics simulations. And here we'll mainly focus on what we did for the data-driven surrogate modeling and model discovery for hypersonic applications. So our work can be classified into these fluid structural thermal interaction problems. This is a typical problem that would happen in hypersonic flight. Here is an example of what we would expect for the skin surface of the hypersonic vehicle when it is exposed to the hot and chemically reacting hypersonic flow. And here's one more interesting example where we studied the control surface mounted on a cone surface. And this cone surface and this panel is compliant and it is subject to the impingement of the shear flow, the flow separation, and the shock impingement. And a lot of interest physics can happen in this process. So specifically, here are some physics we mainly want to look at. One is, of course, the hypersonics aerothermodynamics, where we have a lot of real gas effect and viscous shock interactions, turbulence, and also like flow separations. And also we have, of course, the structural dynamics, the response of the vehicle structures. And here it might have a lot of different instability behaviors like flutter and buckling. And finally, we also have a heat conduction problem because the hypersonic flow is so hot around the vehicle and the structure might be heated up and we might be seeing material degradation and also the ablation of the surface. And all these physics doesn't stand alone. They interact with each other with the physical quantities being transferred to each other. Now, one more issue in this FSTI problem is that we have a huge disparity of the time scales. For the fluid structure thermal problems, they are having a short time scale, while typically we need to simulate the vehicle for the entire flight time. However, so far we mainly can only do two things. Either we use some low fidelity model and do this long-term simulation. However, this kind of simulation can lead to some wrong results. Or we can do high fidelity model, but using only look at a short time frame. This can be done fairly easily. However, what we really need to do is to do the long-term simulation over high fidelity models. Only that can give us a very accurate prediction of the behavior of the hypersonic vehicle. However, the issue there is that given the requirement to resolve all these transient physics, it can take weeks or months to finish the simulation. And this is mainly intractable for the design of a hypersonic vehicle. So the essential bottleneck in this simulation is the aerodynamic solver, where the aerodynamic solver should take the surface deformation of the structural solver and the surface temperature from the thermal solver, and then given the deforming surface, the aerodynamic solver will return the pressure and the heat flux acting on this surface. And then these pressure and heat flux loads will be transferred back to the structural and the thermal solvers. And what we initially did is to replace the CFD-based aerodynamic solver using a surrogate solver. And this surrogate solver is essentially an interpolation model. It takes the input, namely the surface deformation and temperature, and return the pressure and heat flux distribution. This input and output relation is data-driven. It is determined using a data set of pre-computed CFD-based sample solutions. These solutions are associated with different surface deformation and temperature distributions. And then from the input to output, we use some technique of Gaussian process regression, or known as kriging, for the interpolation. We also used some dimension reduction techniques to reduce the size of the data and making this interpolation more efficient. Doing this trick can accelerate the aerodynamic solver by 4 orders of magnitude. What has to be done in minutes to hours now can be done in milliseconds. However, this is not enough for our study. In this surrogate approach that we described just now, it only works for a fixed state. By state here we mean for geometry and fixed flight conditions. So we could do a surrogate for a certain geometrical configuration at a certain flight conditions, which requires maybe 1,000 CFD solutions. However, in reality, we might want to analyze the hypersonic vehicle for several situations, for different geometric configurations, and for different flight conditions. If we have to do 1,000 CFD solutions for each combination of these conditions, then it is intractable again because of the heavy offline computational burden. So what we developed is a transfer learning technique where we started with a reference surrogate which is generated for a specific geometric configuration and a flight condition. And then we introduce a certain correction factor, and this factor will correct this reference surrogate to a new surrogate which represents the surrogate for a different geometry and a different flight condition. And this correction factor, unlike the conventional techniques in the machine learning community, we found this correction factor using an analytical approach based on some physics-driven engineering models. And this way gives us a very simple correction factor, yet it is very effective, that spans over several certain envelope of combinations of geometry and flight conditions. And with this technique, we are able to reduce the cost training by 90%. And we wanted to make the surrogate even more efficient, because ended up with another problem. We have our RANS solutions. They are high fidelity but quite expensive to generate. Conventionally, we just do maybe 1,000 solutions and make some interpolation, and then we generate a surrogate for the aerothermal load that is used in our fluid thermal structural interactions. However, we would encounter this problem of curse of dimensionality, because our surrogate, as an interpolation model, it is just exploring the parameter space of our interest using the number of samples that we give to the model. And this number of samples is increasing in a exponential or polynomial order, depending on the number of inputs. This means this surrogate model is really difficult to apply for very complex problems. By complex here, we mean, for example, geometric configuration that is very complex, involving very complex deformations that is hard to parameterize. And then here we, if we have so many parameters, then we would need too many Rance solutions that are intractable to generate for a practical amount of time. And here we introduce this multi-fidelity model to resolve this issue. So instead of directly generating these 1,000 solutions from a Rance solution, we take another low fidelity model, but it's efficient to evaluate, and then we compute a lot of solutions from this low fidelity model. And then we just get maybe 10 or a dozen of high fidelity solutions from the high fidelity solver. And then we use this data assimilation technique called multi-fidelity Gaussian process regression. This mixes these two sets of data and again generates a high fidelity and efficient surrogate for aerothermal load that we are looking for. And in this process, we basically almost eliminated the cost for doing the expensive Rance solution, and yet still is able to achieve some result that is as if we are using 1,000 expensive CFD solutions. And here's an example. We are trying to predict the heat flux on this panel, and this panel deforms in a sinusoidal form. And here are the input of our samples that we chose. We used these blue dots, which are low fidelity data, while these red crosses are the high fidelity data. As you can see, there's only a fraction of high fidelity data within this parameter space. And if we are only using this high fidelity data, we would never find the correct heat flux prediction. Now here is what we get for the multi-fidelity simulation. This is a high fidelity result as the test case, and you can see that here the low fidelity data or prediction can capture the correct trend, but the peaks are totally off, which is actually important for FTSI problems, because concentration of heat flux can result in a very catastrophic local buckling of the structure. However, using our multi-fidelity technique, we are able to correct this trend and result in a prediction that is almost identical to our high fidelity dataset. Okay, so that's enough about the surrogates, and we indeed have achieved some success using the surrogates by accelerating the aerodynamic solver and by reduction of the training cost, so that the surrogate is very or somewhat generalizable to some cases. However, it still has some limitations. One thing is that the model is not interpretable. It is just an interpolation, and it doesn't learn anything from the data, because now it's just a black box. And second, it is not that generalizable, because it cannot handle the unseen scenarios. For example, if I have a different input parameter to the surrogate, then it doesn't know how to deal with this kind of input. And finally, even though we have developed this multi-fidelity approach, it still requires a lot of training data, whether it's low fidelity or high fidelity. And therefore, it is still not efficient enough. So therefore, we went beyond the surrogates and wanted to look at this data-driven model discovery approach. That is to say, in the past, we have been deriving analytical models by hand, resulting in the Navier-Stokes equation, for example. How about now let the machine learn some physics from the data, or learn some physics can be used to generate a model, and use such that we have the model to predict our physical response. So this is our trial for the hypersonic problem. We started with a first principle modeling called the turbulence viscous interaction model. This is actually a very classical model from the 1970s. It does respect the physics, because if you can see, it's essentially a momentum boundary layer equation, and it is a system of differential algebraic equations. In the past, it is only able to approximately find the pressure distribution in hypersonic flow, because by then people have to solve it analytically or by simple numerical methods, and cannot therefore handle some physics. For example, the high temperature effect would be missing in this first principle based simple model. And now we want to augment this model by some functional correction terms. The missing physics can be seen as we are not modeling some of the parameters in this model accurately. For example, here we are looking at the shape factor of the boundary layer and some Mach number variable in this model. And now, with the introduction of these corrections, we end up with a new DAE system with unknown functions. Note that now it is not unknown values, it is unknown functions. And then how do we identify these unknown functions? We would use the data, the high fidelity data, or this can be from run solutions or direct numerical simulation data, or even experimental data. We learn these functional forms by a constraint optimization problem. It looks like this, which might appear complex, but it can be solved efficiently by a method called the adjoint method. And then with this approach, we are able to find some functionals to make this simple model as accurate as, for example, the RANS solution. And also, it can capture the relevant physics, and from the functional form of this data, it is also interpretable. So here is a detailed flowchart of how we did this augmentation using the neural networks. So starting from the initial stage, we always had this trade-off problem. We either have a high fidelity but expensive solution or solver. We also have a low fidelity but efficient to evaluate model. In our case, it's a TBI model. And then in the first stage, we first identify the optimal correction terms for specific cases of the RANS solutions. And then next, we try to generalize these optimal corrections for arbitrary cases. And this is where the neural network comes in to use the data from stage 1 to generate a network representing the functional correction terms. And finally, with these functional correction terms, we are able to reconcile the conflict between the high fidelity solver and the computational efficiency, where we end up with this augmented TBI model. And here is some representative results. Here we considered a flight condition, and then here are the functional corrections that we found. And then first, this dashed line are our classical integral equation, and apparently it's predicting a pressure that is off from our true RANS solutions in red. However, using the optimization and correction approach, we are able to capture almost exactly the pressure for the RANS case. Now, in summary, we have talked about a toolbox for the bottleneck of multiphysics simulations, namely the aerodynamic solver in our context. We used the surrogate modeling approach, which is essentially a regression model with some dimension reduction technique. And this basic model already achieved an acceleration of 4 orders of magnitude. We further enhanced the performance of surrogates by making it extrapolative using transfer learning. This way, we can use just one model for multiple different cases. And further, we introduced some data assimilation technique called multi-fidelity modeling approach. And this way, we are able to achieve the same predictive accuracy with much less high-fidelity samples. This would make our model generation extremely efficient. And besides the surrogates, we have also presented a data-augmented physics model, where we started from some first principle-based models, which is in fact derived even half a century ago, and we are able to revive it into the basis of a high-fidelity model by using the embedding of neural networks and just a few RANS solution data. And for the new model, it becomes very generalizable and also highly interpretable. And this concludes the presentation of our methods or methodologies in the past and the current research of APUS lab at Penn State. If you are interested in knowing more, please see our website apus.psu.edu.